Hey Ash. Okay, knapsack. The 0, 1 knapsack. All right, let's get into it. So, what is this algorithm? All right, we got a thief. It's got a magic knapsack. You can put any size object into it, but there is a weight limit. So, uh, our thief is going in their house, and he just wants to maximize the value that he puts in the knapsack. So, let's see how we can do this. Let's make a new file. We'll call it knapsack.py. Now, what can I tell you about the knapsack problem? It is what's called NP-complete. I used to think that stood for non-polynomial, but it stands for something more complicated. And the bottom line is, it means there's no formula to solve this problem. You just got to try every combination. So we want to be efficient when we do it. And this video, we will not, but we'll fix that in the next video. So now you might be thinking, well, gee, we have a small item like a ring, give it a value of 1,000. It has a weight of 1, whatever weight unit. So we should take things that are small but valuable, and so we could just divide the value by the weight of all the items, and we'll just sort them in descending order and just start filling up the knapsack, and then we'll have the best total value. What do you think, Grumpy Cat? Will that work? No. Alas, when you have a few number of items, a lot of the examples you'll think of might work, but it doesn't work. Once you get a large number of items, it never works. And here, I'll give you an example. When just 3 items, if our weights are 10, 20, and 30, and our values are 60, 100, and 120. I'll get them all lined up. These are what are called parallel lists, because like item 0, its weight is from this list. The 0 index of this list, its weight is 10, and its value is 60. So there are many ways we could represent the items, but using parallel lists is a common way to do that. I'm just going to make these comments. That will be part of our code. So basically, why is it called the 0, 1 knapsack? Well, that's because 0 means the item is not in the knapsack, and 1 means it is in the knapsack, because for every item, those are the only options. And how do we choose? Well, we want the choice that gives us the best total value. So that's why I taught you about recursion, because we can actually write that. So if we put it in the knapsack, our value will increase by the value of the item. So the value of the item, we'll just write in pseudocode here. This value item plus our function, we're just going to call it f for now. And we'll put in our 2 parallel lists, always going to be the same. And I forgot to tell you that the capacity here is 50. Yeah, that makes a difference. So that's why you could see that, because they're actually in the order of biggest ratio to smallest. So if we use that ratio method, we would take the first 2 items with these values. But as you can see, the capacity is 50. So what we really want are these 2 items. That'll give us the best value. So, and then we will keep passing the capacity. But if we take an item, the capacity of the knapsack goes down. And how much does it go down? It goes down by the weight of the current item. So there's that. And then we need to move on to the next item. So we'll be looking at I plus 1. I is our index. And yeah, so that's if we keep the item. Now, what if we don't keep the item? Well, then we just move on to the next item. Couldn't be easier. In fact, I'm just going to copy and paste, and I'll fix up, and we get rid of this because our capacity does not decrease at all. So those are our two choices, and we just want whatever one ends up being the biggest. And if we have two values, Python has a little convenience function called max, which will return the biggest of the two. So we can just write max of these two choices, and we're done. We'll write it up formally in a second, but let's take a look. This time I've done the drawing ahead of time. But let's go through how we filled this in. So here's our first choice. Now remember, here's what we're looking at. So this is what, because we have two options each with each run through the function. And so this creates what's called a binary tree. And you can see the tree gets crazy fast. This row here has 8 items. So that's 2 to the number of items, 2 to the 3 here. Well, let's say you have 10,000 items. That's 2 to the 10,000, which is really big. I looked it up. The number has 3,011 digits. So that's why we're going to fix the efficiency in the next video. But we're still going to use the same technique here. And so we have our first choice. If we keep item at index 0, our value is going to increase by 60, and the knapsack capacity, big W, is going to decrease by 10. So then the starting capacity is 50, so the capacity will now be 40. All right. If we don't put the item in, there'll be no change. We just move on to the next item. So same thing here. If we now take the next item, from here, we add 100 to our value, and we decrease the capacity, which will now be 20. Over on this side, where we didn't take the first item, but say if we take the second one, we'll increase our value by 100, and our capacity will now be 30. And we keep going. Now we come here. Oh, and here's a check I didn't talk about. Before we get to this point, check if item fits. If not, then we're not going to take the item, obviously. And I just got to check my phone. I got a message. Okay. And of course, before that, we need to check our terminating condition. I'll put check terminating condition, which will be if our index is equal to the length of, and these two lists up at the top here are the same length, so we can use either one. I'll just use the first one. It's equal to the length of the weights. Then we're done. Or another one is if the capacity is 0, then we're also done. Yeah. So here, back here, our capacity is 20, but you see the weight of that last item is 30, will not fit, so we ain't taking it, so no change. Here, we took the first item, didn't take the second, taking the third, so we add 120, and we decrease the capacity, which is snow, which is now, well, you know what I'm trying to say. 10. Here we didn't take it, so no change. All right, here didn't take the first one, took the second one, took the third, so we add 120. The capacity's down to 0. Here we didn't take this last item, no change. Here didn't take, took. All right, then we get to I equals 3. So the index is equal to the length of the list, and we return 0, and we can start backfilling these things. So here, 0. So both of these are no change, so both of them will be 0. This one, add 120, so it'll be 120. This one, no change, so it's 0. This one's 120. This one's 0. This one's 120. This one's 0. So only the max moves on. So here they're both 0, so we're going to return 0 up to here. So add 100. So this is 100. So here, which is the winner? 120. And there's no change, so we'll just move the 120 up. Now here's 120 gets moved up, and we add 100 to it, so it becomes 220. And here we have the max here is 120, so that moves up. Nothing, no change to it. So next round, we have 100 versus 120. Well, 120 is going to win. It says add 60, so now we're at 180. And 220 versus 120, well, 220 wins. And 220 versus 180, 220 wins. So there it is. It's 220. And we can see we got that from the last two items. But also, we'll notice that when we write it up, we're not going to know which items we actually used. We will fix that so there'll be 2 more videos. So the next video will make it more efficient. And then the last video will actually do it in a way where we keep track of which items we actually used, that we actually put in the knapsack. Okay, but let's do some coding. So we want to make a function. And how about we call it knapsack rec for recursive. And we are going to take these lists, the list of weights and list of values, and the capacity of the knapsack, and our index, which will give a default value of 0, and the colon. And so we need to check terminating statement. So if I is equal to the length of W, then return 0. Okay. Now, if the item doesn't fit, if the weight of the current item, so it's W sub I, is bigger than our current capacity, then re-return, we just move on to the next item. So it's knapsack recursive, and WV, and W, and next item. Boom. Look at that. And then, so we already said, so if we keep the item, our value increases. So we'll return, and we said it'll be the maximum of, do we keep it or do we not keep it? So if we keep it, our value goes up by the value of the current item. And then we run the function. Same weights, same values, but our capacity will be decreased by the weight of the current item. And we move on to the next item. So that's option 1. Oh, I forgot the name of the function there. It's knapsack rec. So our other option, not to take the item. It'll be, you just run the function. Same weights, same values, no change in the capacity. Just move on to the next item. That's it. So let's use this function. So actually, we will, let's see, we will say, we'll give it a value. We'll call it total value, val equals knapsack rec, and we'll give it that list of weights, 10, 20, 30, and we'll give it a list of values, 60, 100, 120, and the capacity is 50, and that's it. We'll use the default value for our index of 0, and then we will print val. And we're saving it, and let's see if it works. 220. Woo. Okay, this run before I was just messing around with some other code, so pay it no mind. But so there it is. It worked. All right. Next time, making it more efficient. All right. Bye.